Welcome. Let's take a look at this example. So 2 English classes with the same number of students took a final exam. The side-by-side box and whisker plots summarize the test scores for each class. So side-by-side box plots just means we have 2 box plots using the same number line. So for the purposes of comparing 2 different groups, we can create these box plots together. So I'll go ahead and just label the components that make up a box plot here. So starting with the box, the left side of the box is Q1, the right side is Q3. So that's the box part of a box plot. That line inside of the box is Q2. And just a reminder, Q2 is equivalent to the median of the data set. So remember, median, or down here, median means that about half the class got lower than that value. Here, that would be, it looks like 67. And then the other half of the class got higher than that value. All right, and then the whisker part, the left whisker ends at the lowest score. The right whisker ends at the highest score for each of these groups. Okay, and then we can answer many different questions here, but we'll start with our A. Which class had a smaller interquartile range? So remember, the IQR interquartile range is just the difference between the third and the first quartile. So the IQR, Q3 minus Q1, represents the length of the box. So without even doing a calculation, I can see that the IQR, the length of the box for class A, is definitely smaller than the length of the box for class B. So the class with the smaller IQR was class A. And then which class had a lower median test score? So the median here for class B is smaller than the median for class A. So that would be class B. And then we're going to describe shapes. So for class A, that graph is actually perfectly symmetric. The whiskers are the same length, and the left and right sides of the box are the same length. So we don't always talk about perfection, but that one is perfectly symmetric. I'll just abbreviate there. And then for B, class B, that group of students, the right whisker is longer than the left, and the right side of the box is longer than the left side of the box. So that creates our skewed to the right shape. All right, and there you go. So putting them side by side just gives me a quick way to compare how the 2 classes did. I'm going to add one other piece of information here. We started with the IQR interquartile range. We could have also just discussed regular range, which is high minus low. So I can see here the difference between the highest score and the lowest score in class A is smaller than the difference between the highest score and the lowest score in class B. So just a reminder that interquartile range is the length of the box. Regular range is the distance from whisker to whisker. All right, so let's move forward now. Next, we're going to get back to the concept of outliers. And sometimes data sets do have outliers present, and that's what we'll step through next. All right, so I'm going to jump in here with an example of a baseball player, Roger Maris, and he was an American professional baseball right fielder. He played 12 seasons in the major leagues and is best known for setting a new Major League Baseball single season home run record with a total of 61 home runs in the 1961 season. So the question is, was his record-setting 61 home runs Was that outside the general scope of his other seasons? In other words, was 61 unusual for him? So was it an outlier? So an outlier is a number that's quite different from the rest. And so I've written here his season home run totals for the 12 seasons he played. And I went ahead and put them in numerical order for us. So here's his record-setting 61, and we're wondering if that is unusual, so quite different than the other seasons that he played. So just looking at it subjectively, just based on our own opinion here, 61 does seem like a pretty big jump from his next highest season home run total, but we want a mathematical way to decide if we're going to consider it unusual enough, different enough to designate it as an outlier. All right, so before we deal with outliers though, let's just go through again a regular box plot. So regular box plot means that we don't discuss outliers, we just graph the 5-number summary. So I've got my 12 values here, so let me find the median. So the median would be between the 16 and the 23. So cutting that list in half, so there's our Q2. And then I have 6 numbers to the left of that. So if I go to the middle there, between 9 and 13, that will be our first quartile. On the other side, we'll have our third quartile. So the minimum value is 5. And then Q1 will be the average of 9 and 13. So you can do that on your calculator if you would like. Just add the 9 and the 13, divide by 2 to find that average, which is 11. And then for the median, we'll take 16 plus 23, average by adding and dividing by 2, and that is 19.5. And then finally, Q3, we would average the 28 and the 33. So add and divide by 2, 30.5. And then our maximum value would be that 61. All right, so at the bottom of the page here, I've graphed the regular box plot. So there's the 5 for the whisker, and then the 11, 19.5, and 30.5, and there's the 61. So let me just label down here. That would be the whisker endpoint, and then our Q3 is at 30.5. Now, when we graph a box plot and we see quite a long whisker, it's an indication that we may want to consider 61 as an outlier, so something very different from the rest. So if we decide mathematically that 61 should be designated as an outlier, what we'll be doing is modifying our box plot. It's called a modified box plot, to use a special symbol to designate that value of 61 as an outlier. So there it's just a little rectangle, but we need to step through the math on how to determine if that value is an outlier. All right, so let's start with actually finding the interquartile range. So the difference between Q3 and Q1, so 30.5 minus 11. Now, just coincidentally, this is 19.5, which matches the median, but that's pure coincidence. So that's unrelated. That's just our IQR. So the difference between Q3 and Q1, the length of the box. All right, so to check for outliers, we're going to look for any data values that are more than 1.5 IQRs. So 1.5 IQRs below Q1, or more than 1.5 IQRs above Q3. Any values beyond those numbers are called outliers. So what we'll do is we'll create some boundaries, and any values that are outside of our boundaries will be our outliers. So I'm going to switch color here so you know that these aren't data values that we're talking about. They're just these things called the boundaries to help us identify potential outliers. So we're going to take our Q1 value, that was 11, and we're looking at values more than 1.5 IQRs below that. So by subtracting, we go below it and we take 1.5. The 1.5 is just part of the formula. So 1.5 times, I'm going to put an asterisk for times, the value of our IQR. Versus our upper boundary, we'll take our third quartile, 30.5. And now we're going to go above it by adding 1.5 times the value we got for the IQR. All right, so I'm going to enter it exactly like I wrote it. So order of operations, the multiplication would come first, and then you do 11 minus that product. So the calculator knows order of operations, so you can just enter it like I typed it or wrote it. So 11 minus 1.5 times 19.5, that brings me down to negative 18.25. And then for the upper boundary, 30.5, add 1.5 times IQR. And that is 59.75. All right. So let's talk about these boundaries. So I'm going to go back and look at my data. And the smallest number here is 5. So a boundary of negative 18.25 on a number line would be over here somewhere. So we don't have to draw this part to scale. We just want to know that our lower boundary is somewhere below 5. So I'll just write LB, lower boundary, negative 18.25 on a number line would be somewhere left of 5. And then our upper boundary, 59.75. So on a number line, that would be somewhere here between 39 and 61. So there's our upper boundary. All right, so any number that's not within the boundaries is designated an outlier. So now I can see that 61 does fall beyond the upper boundary. It is outside the boundaries. So that value is considered an outlier. And we'll use a special symbol to identify it when we do a modified box plot. And I will generally use an asterisk for that. The symbol doesn't really matter. Down here, it's a little rectangle, but some symbol to tell people that we consider that different enough to designate it as an outlier compared to his other seasons. All right, on the low end, there's no values that are falling beyond the lower boundary. So our only outlier here is our 61. So the only last thing that we have to think about now is what are we going to do with the whiskers when we do a modified box plot? So we've decided that 61 was an outlier. So if we use a special symbol for that and we want to continue graphing our data, we need to talk about our whisker. So it's not going to go to 61. That one is sort of removed from possibilities. So his next highest home run total was 39. So that's going to be our new whisker. So I'm just going to circle it here. So the highest number that's not the outlier becomes your whisker. And on the low end, the 5 there, because there is no outlier on the low end, that's going to be your lowest value still. So that's still your whisker on the left. So on the modified box plot, left whisker didn't change. We don't change Q1, Q2, Q3, but if we do have an outlier, that whisker now ends at 39. Okay, so on our graphing calculators, you always have a choice. You can graph a regular box plot or a modified box plot. So there's no rule that if you have an outlier, you need to identify it. So we always have this option on which type of graph we would like to display. But now people know that we would consider his 61 season home run total a bit out of the general scope of the rest of his seasons, and his remaining seasons are identified by the box plot, which is created by numbers that are inside of our boundaries.